I'm Paulo Carey, and this is my creative assignment number 1, which is the lecture assignment. And today I'm going to be talking about orbital velocities, specifically orbital velocities for circular orbits. So we know that orbital velocity is given by the equation v equals square root of g m over r, where g is our universal gravitational constant, m is the mass of the body that we're orbiting, and r is simply our orbital radius. So we can actually use our known polar velocity and acceleration equations of motion to derive this orbital velocity formula. But first, we need to introduce a few assumptions here. So we are assuming that our orbits are circular. Meaning there's no, elliptical orbits, just purely circular. So what that means is our radius, is constant, meaning we have no change in radius, meaning we have certainly no acceleration along our radius. And we do have an angular position, and likewise we have an angular velocity. However, since orbital velocity is constant with circular orbits, we have no angular acceleration. So what that means is we're left with these three terms, while all the other terms go to 0. So we can actually use this to derive this equation using our known polar equations of motion. So we know from in lecture that v of t is given by r dot t er plus r of t theta dot t e to the theta. And we know that a of t is r double dot t minus r of t theta dot t squared. That's for er. And then for our e theta term, we have 2r dot t theta dot t plus r of t theta double dot t. And that's for e theta. So what we can do now is we can go ahead and cancel out all of our terms that do not have any value. For example, here, we said in our other slide that r dot is 0. So this entire er term is 0 now. And we still have an r and a theta dot, so we're still good there. That term exists still for v. Now, for the acceleration term, we saw that r double dot is not 0, or is 0, so that's 0 there. rt theta dot t, still good. And then for our e theta term, we have no r dot, so 0, and we have no theta double dot, so 0. So what we're left with now is v of t equals r of t theta dot t e theta, and a of t is left with negative r of t theta dot t squared. E theta. Now this makes sense really, because if you have a circular orbit, you're not moving along the radial direction, so you would expect there to only be a velocity term along theta. And kind of likewise for, I just realized that's e of r, not e of theta, my bad. Likewise for our acceleration term, since we don't have an angular acceleration, we wouldn't expect there to be an acceleration along the theta term, so only along the r term. So now, if we put these into magnitude form, so v equals r theta dot and a equals r theta dot squared. These are magnitudes, hence why there's no negative now. What we can do, our first step here, is to arrange for theta dot from the acceleration term, because we know the actual acceleration here, because acceleration is just g, and g is gm over r squared. So we can actually go ahead and arrange for a, and if we sub in g, we have gm over r squared equals r theta dot squared. Now what we can do here is we divide everything by r, so then we get gm over r cubed, take the square root. This is theta dot. Let's go ahead and mark this, because this is a pretty useful term too. This tells us our angular velocity in terms of radians per second, which we can use dimensional analysis to subsequently find out the orbital time, the time it takes to complete one orbit. So we're going to keep that equation handy. So now, if we take theta dot and we plug it into the v term, that's our orbital velocity. So what we have now is v equals r times the square root of gm over r cubed. That r turns into an r squared when we put it inside the square root, which cancels out with the r cubed on the bottom, leaving just a singular r down there, which means this is going to be gm over r equals v. And what do you know? That's our orbital velocity. Now, there is one more little simplification here that we can do. Like, what if we don't like using the gravitational constant, and what if we don't know the mass of our big body that we're orbiting? However, what if we know the acceleration due to gravity on the surface? So what we know is that g naught is gm over the radius of our object squared, because on the surface, which is at our radius for our object squared, we know g naught. So what we can do is arrange for g, which means g here is going to be g naught rob squared divided by m. And now if we plug in g to our two equations, or three equations, we can even do it for our gravitational acceleration term here. We see that g equals, the m's are going to cancel out, so it's going to be g naught r object squared divided by r squared. So that's g in terms of object radius and gravitational acceleration at the surface. And then if we plug it into our angular velocity term here, we see theta dot equals, once again, the masses will cancel out. So we're going to have g naught rob squared divided by r cubed. And then if we do it for our orbital velocity term, what we see is that v is going to equal, the masses will cancel it again once plugging in, so we're going to get g naught rob squared divided by r. So these are three little handy useful formulas here that we just derived using our known equations from lecture. So now, what we can do is we can do a practice problem using known data from the ISS, including its orbital altitude and the radius of the Earth. So what we can do here is, let's go ahead and get, first of all, I don't really like kilometers personally, so let's go ahead and get this like kilometer nonsense in terms of meters. So we see that our orbital altitude is going to equal, I'm just going to call it r, is going to equal 1,000 times 415 plus 6378. And this is going to equal, let me go ahead and plug this into my calculator here. It's going to equal 6793000 meters. And now we need to know the radius of the Earth in terms of meters. This is going to equal 1,000 times 6378, which is going to equal 6378000 meters. So now that we have everything in terms of units that we like, we can actually use our equations prior to start solving this problem. So part one is asking for the magnitude of acceleration, which we know is just g. And g, as we stated earlier, in terms of the variables that we know here, is g naught re squared divided by r squared, which is going to be 9.81 meters per second squared times 6378000 meters squared. And then we're going to want to go ahead and divide this by 6793000 meters squared. So what we see here is that the meters squared in the top and the bottom are going to cancel out, and then we're just left with meters per second squared, so the units still check out. And what this is going to equal, once I plug this into my calculator here, it's 9.81 times our radius squared, so that's going to be 6378000 squared, and then we're going to divide all that by our orbital altitude term squared, which is going to equal 8.65 meters per second squared. So we know this to be the magnitude of our acceleration. Excuse my constantly changing notation. I can't seem to make up my mind whether I want this form of notation or if I want just regular A. So, and this has been something I've been battling for years personally, but usually I prefer having this notation here, but for the sake of simplicity earlier, I just left it as V's and A's without any, magnitude signs. So that's our magnitude of our acceleration. The magnitude of our orbital velocity, as we found earlier, V, is going to equal the square root of g naught re squared divided by r. So this is going to be g naught re squared divided by r, which is going to equal 9, that's not a 9, that's going to equal 9.81 meters per second squared times the radius of the Earth, which is going to be 6378000, square that, and then we're going to divide that by our orbital altitude, orbital radius, I should say, 3000 meters. Now what we see here with our units is that we're going to have meters squared divided by seconds squared, and then we're going to we're going to square root both that, which is just going to leave us meters per second. So now, what we can do here is we just plug this into our calculator again, 9.81 times 6378000 squared, and divide that by our orbital altitude, orbital radius, sorry, I keep saying that, 3000, and then we square root that number, and what we get here is we get an orbital velocity of 7664.6 meters per second, or approximately 7.7 kilometers per second, which actually, if you look at the data given by ESA, this is actually pretty spot on for our orbital velocity, so the math checks out here. Now let's go ahead and get the magnitude of our angular velocity, which is theta dot, and as we saw earlier, theta dot is just square root of g naught, r object squared, divided by r cubed. So this is going to be g naught re squared divided by r cubed, which is going to equal square root of 9.81 meters per second squared times radius of the Earth, 6378000 meters squared. And then we divide all this by our orbital radius cubed, 793,000 cubed. And what this will show us is that theta dot is going to equal, once I plug this into my calculator, 9.81 times 6378000. Divide this by 6793000 cubed. And then we square root that. And then what we get here is our angular velocity is 0.00113 radians per second. And now, we can actually use this term here for our last part of the question, finding out the time it takes to complete one orbit. So what we know is that one orbit is one circle, which has 2 pi radians. So what we can do here is we just got to do some dimensional analysis. So we get t is going to be 2 pi radians, and then we just simply want to take this term here, plug in up here, we're going to do 1 over 0.00113, because what we have here is we have the radians down here, and we have the seconds up here, so this and this are going to cancel out with, and we're just going to get 2 pi divided by our orbital velocity, which is going to give us, 2 pi divided by orbital velocity is going to give us 5,569 seconds, or approximately 93 minutes. And if we look once again at the data provided by NASA, this is also pretty spot on. So the math checks out. So this is orbital velocity derived and applied using our equations that we learned in class. And here are my references.